Hey, grade nines. We're back again today discussing topic 2.1 of the electrical unit, which is controlling the flow of electrical current. Today, I want to discuss the significance of conductors and insulators, which we've already discussed, and the topic of what we call resistance in an electrical circuit. Now, in earlier lessons in this unit, I discussed the components of a circuit. You require a conductive wire, you require a load, you require an energy source, and you require a switch. Well, we also discussed in the electrical safety section of the unit, 1.3, we discussed the significance of making sure that wires in a circuit have insulators around them to prevent short circuits from occurring. I'd like to discuss sort of what is actually happening with these conductors and insulators and why they do what they do. So first of all, let's discuss insulators. Insulators, by definition, do not conduct electricity. They do not allow for the movement of electrons. Now, substances that are insulators, again, you should be familiar with this. We've discussed this before in this unit, and we've also discussed it in Unit B in the chemistry unit, that insulators include nonmetals. Water, in a pure state, water does not conduct electricity because it's a molecular compound, non-metal. We also have ionic compounds. When they're not dissolved in water, they also do not, generally speaking, conduct electricity. For example, salt. If you have salt on a table in a solid form, it's not going to conduct electricity. Now, why is this? Well, these substances generally tend to have electrons that are they're bound very tightly to the nucleus or the nuclei of the molecules or the atoms that make up the molecules. So these electrons do not want to move very much. And when they don't move, we know that electricity is all predicated on the fact that electrons are going to move from one place to another. Otherwise, if you can't move a charge, you can't produce an electrical current. So insulators, by definition, do not move electrons, so that's how they don't, I guess, propagate electricity because of that, because their electrons are bound tightly to their nuclei, and they don't, those electrons don't move. On the opposite end are obviously our conductors. These are the ones that actually comprise the wires that make up the electrical circuits. You should know, again, that these are ones that do conduct electricity because they allow for electron movement to occur. They include metals. They include ionic compounds that are dissolved in water. They also include your acids and your bases. So these are all great conductors of electricity. Now, what makes them great conductors of electricity? Well, unlike insulators, the electrons in these substances, in these atoms, in these molecules, they are free to move. They are not bound tightly to the nuclei, and they can move at will. So because of that, these electrons can now move through circuits. They can move a charge from one location to another, which would allow us to produce that electrical current that we require in order to power things in our homes, right? So that's what conductors do. Now there's a lot of good metals out there that will conduct electricity. One of them would be copper. Gold is another good one, a lot more expensive, and silver is another good conductor as well. Before we discuss our next topic, I'm just going to get you to quickly review up here. Just take a quick peek about what makes a conductor, and an insulator, before I move on to my next topic, which is going to be superconductors. Now, what a superconductor is, other than it sounds like a great superhero, superconductor man or whatever, but superconductors are conductors that literally have there's no resistance to the movement of electrons. These are metals that are so good at moving electricity that there's absolutely nothing that can literally stop the electrical current from moving. And there's been a lot of research done into superconductors because as far as energy requirements, if we could move electricity over great distances, from power plants to other parts of a province or even another part of the country, one of the issues when you're moving electricity over great distances is the possibility of the loss of electricity because of resistance through conductors. Even if conductors are like copper or silver or gold, they over time will lose electrical current. So you lose electrical current because of resistance. Well, if you can create conductors or wires that have no resistance, you can produce electricity, say, in Edmonton, and then send that electricity all the way to somewhere like, let's say, Jasper, 400 kilometers away, and you would literally have no loss of electrical current coming into Jasper, which would be much more efficient. That means we have to burn less fossil fuels to produce the electricity, or we have to have less input energy because we're not losing electrical energy as it moves through a circuit or through a transmission line or whatever. So there's been a lot of research done. One of the early guys that did this was a guy by the name of Ons, who did some work early in the 20th century. But generally speaking, these superconductors have to be super cooled. In order for them to work, they have to work at really low temperatures. Like, for example, when Owens did his work, he worked with mercury. He found that mercury, if you cooled it down to negative 273 degrees Celsius, it became a superconductor. Under normal circumstances, mercury doesn't function as a superconductor, but when you cool it down to extreme temperatures, that allowed it to become a superconductor. So there's been a lot of research ongoing to see if we can create metals at higher temperatures that can become superconductors. So there's a lot of work going on here. And if you're interested about superconductors, just click on the link up here. A quick little video that will discuss about what superconductors are and what the cool applications of superconductors could be moving forward into the future. Now, we've discussed how we can move electricity or not move electricity through a circuit, whether you're either using an insulator or a conductor. There is a way to measure the amount of resistance to electron movement in a circuit. And again, when I use the term resistance, and I've used that term a few times already today, it's referring to resistance as anything that reduces electrical current in a circuit. So anything that is going to prevent the movement of electrons is called resistance. The analogy would be if I have a bunch of kids moving through the hallway at MCHS and they're free to move. Let's say I got one kid in the hallway. Right, they're able to move. They could run out of a classroom and just sprint down the hallway as fast as possible. Nothing's really resisting them as they move down the hallway. Now, what if you add 200 kids at one of the breaks in the school? Now there's more resistance for the movement of students because there's people blocking things in the hallway. And then even worse, what if you're walking down the hallway, then Mr. Bautestein comes up and starts pushing you like this and pushes you back while you're trying to move, let's say, to center court from my classroom and down in 111. All these issues are considered to be forms of resistance. And that's the same thing that happens in an electrical circuit. Anything that's going to stop or block, not necessarily stop it, but just slow down the movement or restrict the movement of electrons. That is called resistance. Now, that is measured in another unit. Now, we've already discussed volts, which measure the electrical potential, the energy of an electrical circuit. We talked about amperes or amps. A, that represents the amount of electrical current. When we measure resistance, which is our third major unit now of measurement in this electrical unit, and we are going to spend more time on calculations for these in one of the sections coming up. I think it's in 2.2. You're going to be using the measurement for resistance. The measurement is called ohms, and it's measured with this horseshoe symbol that represents, I can't remember. It's a letter in the Greek alphabet. I want to say it's the Greek letter for O. Omega. I think it's omega. Yeah, I'm going to go with omega. Yeah, that's the omega symbol because I just remembered that. Yeah, the omega symbol. So ohms is measured. It has the unit, this little omega symbol. And you can actually find the omega symbol in your keyboard. You've got to do like an option click on one. If you know that when you click on your keyboard, and you're going through, you hold the option key down, you get a bunch of other little symbols in there, like the copyright symbol and the pound symbol, if like British currency and stuff like that. One of those symbols, with the option key, is going to give you ohms. So if you're doing this on a keyboard and you want to type out ohms, it is actually on a standard keyboard. If you hold the option key down, if not, just Google it. Pretty much any keyboard is going to give you that ohm symbol. You just have to kind of go digging for it if you're going to do your work on a computer. Now, a circuit can achieve resistance. One of the easiest ways to achieve a resistance in a circuit is putting in a resistor. Now, a resistor is anything that basically resists the movement of electrons. Now, but why would we want to do that? Why wouldn't it be just smart to let electrons run rampant, through a circuit? Well, yes, but what resistors are going to do is they're going to allow you to convert the electrical energy that you're stopping, the current, that energy that's with the current of electricity. You're going to kind of slow that energy down. Well, we know that energy doesn't get destroyed. If I slow down energy, if I stop that energy, it's going to convert into another form of energy. So that's what these resistors are going to do. Generally speaking, a resistor is going to convert electrical energy into another form of energy, which is kind of what we want electricity to do, right? Technically, loads are resistors. A light bulb is basically something that's resisting the electrical flow, and then when that current hits a light bulb, the load in the circuit, it's going to convert the electrical energy into light energy and a little bit of heat energy. And generally speaking, that's what resistors normally convert electrical energy into. They normally will convert it. The most common form when you have resistance of electricity is heat. You will get heat produced as you convert electrical energy. If you slow it down with a resistor, it can get converted into heat energy. But light energy, sound energy, if you're converting, let's say, electrical energy from like an iPod, if you're listening to music, that's what causes the conversion of energy are these resistors. So they are very important on there to have them. And we'll discuss this more as we discuss a little bit more about circuits as we go into the unit. One last thing, actually two last things before I finish this up. This little symbol here that I've got, this little line with the little kind of zigzag lines, that is the schematic diagram notation for a resistor. And we are going to spend more time later in the unit discussing the symbols that you place on circuits in order to indicate that there is a load or an energy source. In fact, I'm going to do a little bit of that on the next board here in about 2 seconds. But every thing in an electrical circuit has a symbol. So you draw what's called an electrical schematic. If you Google electrical schematics, they are like these kind of really cool, like little square things that show you where the resistors are, the switches are, where the batteries or the energy sources are, where the loads are. And every type of thing you put into a circuit has a specific symbol. So if an electrician is maybe wiring a house, if they've got a schematic of how they want to wire the house, they know where to put the resistors or the loads or whatever they need to on the circuit as they're actually wiring a house or a business or something like that. And one last thing I didn't mention earlier, ohms is named after the German scientist Georg Ohm, who we'll be discussing a little bit later in the unit. Just for now, be aware that he came out right around after the time of Volta. He actually did a lot of experiments on Volta's battery, the voltaic pile that Alessandro Volta produced in 1799, which is the world's first battery. Ohm did a lot of research on that battery and then came up with a lot of theories about electricity based on that work and on some other work that he was doing as well. So he's another scientist who had a unit of measurement named after him. Now you've got ampere, volta, and ohm are all early electrical scientists that were involved in electrochemistry that all have units of measurement in electricity named after them. All right, let's finish this up. Okay, so again, if you put a resistor in a circuit, that is going to resist the flow of electrons, and the more resistance that you put in the resistor, the more energy that's going to be utilized outside of the electricity. So, for example, if I want a brighter light bulb, that light bulb is going to have higher resistance. There has to be more resistance in order to make that bright light bulb brighter. So, for example, if you have and I'm going old school here because I know most lights are LED now, but back in the day, you'd have like the equivalent of a 60-watt bulb or a 40-watt bulb or a 100-watt bulb, which represents watts are well, we'll discuss watts later. But for now, just be aware, the higher the number, the more light there is. The 40-watt bulb has the least amount of resistance. The 60-watt bulb has a little bit more. The 100-watt bulb has the most resistance because we're taking more energy from the electrical circuit to make that bulb brighter. So we're using more energy conversion because of the resistance. So remember, a load can be so like, for example, in this schematic that I've drawn up here on the board, here's a circuit. This is my load, my light bulb, which has this cool little symbol there. That's technically considered to be a load, but I could add, if I wanted to, somewhere else in the circuit, if I wanted to slow down the current coming into that light bulb, I could add a resistor there if I wanted to. I'm not going to in this case, but you can see that by drawing that now, I indicate that there is a resistor between the switch now and the load on my circuit. But for now, we're not going to draw that in there. I'll discuss another type of resistor here in about 2 seconds. Okay. Last concept here, and then we're finishing up this topic for today. So for example, again, reminder that, again, a circuit requires a conductive wire. Here's your conductive wire in the circuit. You require a power source, which in this case is a cell. A cell is indicated with a long and a short line. The long line always indicates the cathode of the cell and the positive terminal. And the short line always indicates the negative terminal or the anode of the cell. If I wanted to indicate a battery, that symbol is going to be just slightly different. Remember, a battery is more than one cell. So to indicate a battery, I'm just going to draw that instead. So I'm going to have 4 of those lines now. And by indicating that, I'm indicating that's a battery that's there, not a cell. And these are all these schematic symbols that we'll be discussing later in the unit. But for now, I'm trying to get you used to seeing them so that when we get to that topic, it's going to be a little easier for you to kind of run through all the symbols. And again, you already know the symbol for a switch. I showed you the symbol for a switch in an earlier lesson. Here's a symbol for a light. Now that's a brand new symbol for you as well. But there are, normally we talked about switches either allowing for the flow or not allowing for the flow of electricity. If it's open, there's no flow of electricity. If I close the switch, I close my circuit and then electricity can flow through the circuit, right? Well, there is another form of a switch that you can add, which combines what we talked about with resistors. You can have what's called a rheostat. A rheostat is like a dimmer. If you have a dimmer in your home that dims your lights, that is in fact a rheostat. And a rheostat basically would be indicated. Now, most dimmers still have an on-off switch, right? There is an on-off switch to a dimmer. If I turn on my lights, there's a little bottom switch that would shut the light completely off. But as well, there would be built into that switch what's called a rheostat. Now, a rheostat is what we call a variable resistor. That's the other name for a rheostat. And it has, this is the symbol for a resistor, which we talked about. That isn't a rheostat symbol. We have to add a little bit of another symbol to that. That right now is a rheostat. That's the symbol. You have that little squiggly line with the little line on top. And this represents a rheostat. And that would allow me, in this case, to dim or to brighten the light bulb, right? I could actually have it go brighter or less bright, depending on how much resistance I'm putting into the circuit. Another example of this would be volume settings on your iPod or on your mobile device. When you turn the volume up or down, that is a rheostat that does that. It's a variable, and then of course you could have the actual switch like this, which is the pause button. That would be the switch. So for example, if I had my volume on low and then I wanted to shut, if I had my volume on low, this would be kicking in, but my switch would actually be closed. And then when I go to pause the music to shut it off, that would actually literally open the switch and then stop the actual flow of electricity that's causing you to hear the music. Or in this case, if I open the switch here, I would actually shut the lights. If the lights were dimmed, if I click that open now, the light actually shuts off completely. If you want to take a look at how dimmers work in your home, take a watch of this video right here, a great little video that shows you sort of the science behind dimmers and why they do what they do. And I've just lost my slide here. I hit the wrong button. You know what? This is live, so this happens occasionally. There we go. Hey, guess what? You got some homework. Of course there's homework. There's always homework. Here are the questions for topic 2.1. I'd like you to go over questions 1 to 3 and questions 5 to 10 on page 303 in that good old Science 9 textbook. So until we see you guys next time, have fun with those questions, and we will see you for our next discussion, which will be 2.2, which is going to be discussing modeling and measuring electricity. Exciting stuff, folks. We'll see you then.